In this video, we are going to present the outcome of our final year group project. This will start with a basic introduction to our project, followed by an in-depth look at our individual contributions, and finally, a practical demonstration. Our goal was to design, manufacture, and test the electronics control system for an underwater remotely operated vehicle. This system was developed to compete at the 2020 Marine and Technology Education Competition in Pennsylvania, USA. The competition is joined by hundreds of student teams from universities around the world, each with their own custom ROV, coming together to complete a series of underwater tasks. These tasks vary from testing physical abilities such as collecting plastic pollution, performing pipe inspection, and operating electrical panels, to more complex software operations such as autonomous driving and image recognition. Points are awarded to teams for the number of underwater tasks they can complete within a 15-minute time limit and for the size and weight category their ROV fits into. The first step in the design process was to identify the key functional requirements. These include communication with the surface over a tether, data processing, voltage conversion, viewing multiple camera feeds, taking measurements from a range of sensors, and the ability to control the ROV's thrusters, motors, and pneumatic actuators. Furthermore, a software user interface was required to pilot the ROV remotely. A technical specification could then be developed to make sure our design meets these requirements. To develop this as a team, the system was split into its core components, allocating each member a key part to design. Tight collaboration was necessary to successfully bring each part together to form the completed system. Our design took the form of a physically interconnected modular stack of boards, with each being responsible for a core function in the overall system. The system is mounted inside a watertight enclosure comprised of a data board, a power board, 2 interface boards, and 8 electronic speed controller boards. Let's take a closer look at the design of each board.
The data board is the central control board which handles all of the communications with the surface computer, motor controllers and sensors. This board is equipped with a gigabit fiber optic module which interfaces with the onboard Ethernet switch. This Ethernet switch can also provide power over Ethernet, which allows for up to 3 IP cameras to be connected for high quality video streaming. It is also responsible for up to 10 low latency analog cameras which pass through a switching matrix and are sent differentially to the surface control system. The main controller is the same chip found on the Arduino Duo, an AT-SAM3X8EA, which allows for the use of the Arduino IDE, a piece of software familiar to everyone on the team. As a backup, there is a Raspberry Pi compute module which has up to 4 extra cameras, 2 of them USB and 2 of them CSI. The Duo and Pi are both connected to the Ethernet switch, giving them internet access, allowing for communications to the surface. As a backup, there is also a differential RS422 link to the surface, allowing for low latency UART communications. In order to prevent damage to the electronics, all devices on the board can be programmed from the surface. This means that the tube does not have to be opened, reducing the chance of water reaching the sensitive electronics. To achieve this, the Pi module has a USB hub connected to the Duo's programming port, which, via the fiber optic link, allows the Duo to be programmed from the surface. As a backup, there is an XB wireless UART module, which serves as a way to program the Duo. Multiple onboard inertial measurement units allow for accurate position measurements of the ROV, allowing for the onboard control system to better stabilize the ROV. Temperature, humidity, and total volatile organic compounds are also measured, which allows for the detection of multiple fault types, including water ingress and damaged components. The board is self-sufficient in its power supplying and takes 48 volts direct from the main tether, so diagnostics can be sent back even if it is the only device running. The board also has the ability to monitor all 7 of its onboard voltage rails and has a handy debug screen which allows for quick assessment of the board's performance and general status. As the data board handles high-speed data communications, a major consideration when designing the board was the impedance of the traces. To achieve this, a 4-layer board was used, meaning a large ground plane and power planes could be used. The thin gap between each layer meant that the impedance could be achieved in a relatively small area. The data board communicates with the ESCs on half-duplex RS485 to allow for bidirectional communications with the drivers on a single UART port. This uses a special custom library which ensures that one of the up to 9 devices on the bus talks at once. There are several digital pins that support high-frequency PWM linking to the power board to control the H-bridges and the addressable RGB LEDs used for debugging and lighting of the pool.
The power board is responsible for the aspects of the ROV we would class as high power, whether they demand higher currents or require a higher operational voltage. It was decided that the high power parts would be dealt with separately to the data aspects due to the high current traces that, if run in close proximity to sensitive data lines, could interfere with high-speed communication and sensitive camera signals. The interference comes from the inherent spiky nature of the power demand from the ESCs, which generates EMI. By having separate boards for data and power, the control enclosure can be made smaller with the two boards stacked on top of each other, with interface boards that connect them all together. One of the requirements for the board is to convert the 48-volt power input from the tether down to 2 voltage levels for redistribution around the ROV. Two 12-volt DC to DC converters are used that will each supply up to 5 amps. One is used for external motors and solenoid valves that control external mechanisms required for completing the task in the competition. The second is for up to 10 cameras, which will allow the pilot to see where the ROV is going when in the water and to record video for later use. In order to control the motors and solenoid valves, H-bridge ICs have been used, which can either be used for bidirectional motor control in a full bridge setup or a unidirectional motor or solenoid operation by configuring them as 2 half bridges. This is done via logic level signals from the data board. We also require 5 volts DC to send to the ESCs for further conversion to use for logic level controllers with an additional pass-through to the data board, which allows the 5 volt rails of each board to be connected in the event of one of the supplies failing. As well as this, the board also acts as an interface for the 8 modular ESCs mounted to it. Each ESC controls one of the 8 thrusters used to maneuver the ROV through the water. Each controller requires a 48 volt supply, the 3 high current motor phases, RS485 communication data lines, and a ground plane. The motor traces are each designed and rated to operate up to 7 amps RMS when a motor is operating at full load. Due to this high current demand, 2 ounce per square foot copper was used with the widest possible traces at 1.8 mm to control the temperature within the capsule. It was decided to make the board 4 layers to allow for large ground planes and to ensure routing was possible. With 24 high current traces, all within an airtight container, it was imperative that the heating is kept to a minimum. These parameters mean that there will be a maximum temperature change of 30 degrees Celsius compared to over 75 degrees with a 1 ounce per square foot copper thickness. The most important aspect of the power board design was the modularity of the attached ESCs, using specialised connectors that contain both high current and data terminals in the same package, allowing the easy replacement of any ESC in the event of a fault to make the ROV fully operational as quickly as possible.
The electronic speed controllers, or ESCs, are 3-phase permanent magnet synchronous machine or brushless DC motor drivers for the thrusters. They convert 48 volts DC from the tether to a 3-phase AC sine or triangle waveform which is kept in sync with the thruster motor. To ensure a wide range of options in case of failure, 4 ESCs have been designed. The simplest has an inexpensive Atmega microcontroller to handle the communications with the data PCB and a footprint for an off-the-shelf ESC on the back. As the ESC and the thrusters are designed only for 12 volts, an onboard DC-DC buck regulator reduces the voltage from 48 to 12 volts. The second ESC to be designed is a custom motor driver with gallium nitride MOSFETs for high efficiency at high switching frequencies. The microcontroller on this ESC is a DSPIC 33CH series, dual core with the capability to perform approximately 100 MIPS per core. This directly controls 3 gallium nitride half-bridge modules and gets the current information fed back from 3 INA240 current sense amplifiers. Like all of the ESCs, it communicates via RS485 with the MAX 3485 line driver. The third ESC is a silicon MOSFET version of the previous. It uses the same microcontroller, current sense amplifiers, and even the same software, but has discrete silicon MOSFETs which should result in lower overall losses at lower switching frequencies, around 25 kHz, compared to the GaN ESCs, which can operate at a much higher frequency. The MOSFET drivers interface the microcontroller to the MOSFETs, providing higher current to the gates, and a bootstrapped high-side drive. All 3 of the ESCs so far have an auxiliary power supply to power the microcontroller and peripherals. The fourth ESC is another simple driver. An integrated all-in-one IC from Texas Instruments provides almost all the functionality of the driver, with the Atmega microcontroller and 48-volt DC converter again standing in to provide communications and to reduce the voltage to an acceptable level. The gallium nitride and silicon ESCs have a field-oriented control system written in C and running on one of the two cores. The second core, and the Atmegas on the other two ESCs, handle RS-485 communication and the power status LEDs. The field-oriented controller takes a speed demand into a PI controller using feedback from a PLL estimator. The PI controller adjusts the Q-axis current demand, perpendicular to the rotor, which is proportional to torque. To ensure that the D-axis current matches the demand, a second PI controller adjusts the D-axis voltage to zero the D-axis current, as no field weakening is required. The DQ domain voltage is transformed into the ABC domain and space vector modulated before being sent to the PWM module. Feedback from the current sensors is transformed into the DQ domain to close the current loop. The main function was based on an example by Microchip, however it used floating point maths and the DSPIC33 does not have a floating point unit, so it was rewritten to use fixed point maths over a weekend. Other libraries used were the motor control library, also by Microchip, that contains main function blocks such as transforms, modulation, etc., already written with fixed point maths.
The interface boards are responsible for connecting the electronics control system to all the external devices mounted on the ROV. Each interface board is mounted to one of the control capsule's end caps, where it is connected to the data and power boards via PCI connectors. The underwater connectors mounted on the control capsule are then connected to the interface PCBs, allowing electrical signals to pass in and out of the capsule whilst keeping the electronics dry. The power interface PCB, as its name suggests, handles the high power connections in the system, which are the main power input and the 8 thrusters mounted on the ROV. Due to the relatively high currents flowing through this board, up to 30 amps through the main power input connector, design considerations were made to keep the thermal response under control. For example, 2-ounce copper layers were used, the distance of each trace was kept as short as possible, and the trace width was calculated for the peak current carrying capacity required. In contrast, the data PCB handles connections to the cameras, actuators, data lines, fibre optics and the mini ROV. Due to the large number of connections on this board, JST connectors were used to make maintenance easier. The USB and Ethernet digital cameras, as well as the tether data lines, had to be routed with speed considerations in mind. This involved placing the connectors as close to the source as possible and matching the length and skew of the differential pairs. The software required to operate the ROV takes 2 forms. The first is the code embedded in the electronics control system's microcontroller, and the second is a graphical user interface used by the pilot to control the ROV remotely. Both pieces of software work concurrently to fully control all of the ROV's functions. The embedded program was developed in C++ using the Arduino platform, and its functionality is centered around a custom communication protocol, which uses human-readable ASCII string commands to control the ROV. These commands are received via a serial communication link where they are processed and the required action is executed, such as reading a sensor, moving an actuator, or setting the speeds of the thrusters. On the other hand, the graphical user interface was developed in Python using the Qt application development framework, which runs on a computer on the surface to pilot the ROV whilst it is submerged. The interface is divided into 2 sections, a control panel tab and a configuration tab. The control panel tab contains all the essential controls the pilot requires to operate the ROV during the competition. Since the pilot is not permitted to see the physical ROV, they must rely solely on the onboard camera feeds to maneuver and complete the challenges. For this reason, the camera feeds are the main element on this tab, and the pilot can quickly change between the ROV's numerous camera sources or toggle between primary and secondary feeds. On the right hand side of the tab, core functions such as connecting to the ROV and controller, activating the actuators and displaying the sensor readings are readily accessible. Furthermore, the competition tasks have their own pop-out window, dedicated for adding controls and displaying information specific to that task where required. The configuration tab is where the program is set up, such as setting the number of actuators, setting the address of each camera feed, and configuring the key bindings. Almost every aspect of the program is customizable, and the settings are stored in an XML file, allowing the program to be configured for multiple pilots and future ROV designs. Lastly, extensive code documentation has been written so that further development on the program can be carried out for future competitions. In addition to the original aims of the project, we have also developed an ROV chassis to mount the electronics control system and external devices. The 8 thrusters on the ROV are arranged so that each thruster is offset by 45 degrees to the X, Y and Z axes, providing full 6-axis control. We manufactured a test jig so that we could test the thruster configuration in the water. Furthermore, a surface station was developed as an all-in-one plug-and-play solution to pilot the ROV on location. It is mounted inside a heavy-duty waterproof case and contains a computer to run the control program, 2 monitors to view the ROV's camera feeds, connectors to attach the ROV's tether, and reconfigurable buttons. With all the boards designed, manufactured and tested, we will now perform a practical demonstration of each board and the software functioning to show that they meet the requirements set out.
Right, so here's the setup for the data board. We've currently got it connected to a 48 volt power supply as it would in the competition. There's some slight differences as to how it would be in the competition because we've not got some of the waterproof connectors connected at the moment, but everything that we need to test is currently connected. As for over here, we've got the analog cameras which go through into the analog switcher. We also have the fibre optic which goes through this blue cable here which goes out through the door into the internet. The Raspberry Pi is connected onto the internet which is streaming the cameras and is streaming this power over Ethernet camera here that we can see over there. Over there we can see the Surface computer which is taking the feeds from the cameras and displaying them. We can also see the Raspberry Pi feed that's coming through over there. And finally we've got the LEDs running just to show that we can light the pool up and do the diagnostics.
Hello, this is the ROV setup in a test setup to run the thrusters. We've got a control station. When I press enter, it will send a signal down the tether to Joe's board to run each of the ESCs in turn. These will then run the thrusters and ready, go. It all worked.
The previous demonstrations showed that the power board is functioning as initially designed. With the cameras being powered, we know that the regulator is successfully converting the 48 volts input down to the required 12. As well as this, we know that the modular connectors used for the ESCs are fulfilling their function. However, we can't tell whether the tracers are going to be able to deal with the current and temperature demands the board would experience, as there is no way of simulating how the ROV would operate in the competition due to the halting project progress. Taking a closer look at the output and efficiency of the regulators, we can see how they perform under a varying load. We can see that the 5 volt regulator has a linear relationship in the output voltage, apart from a couple of points at around 0.5 amps. This shows that the controller is correctly regulating the output voltage to keep it around 5 volts. As well as this, we can see that the regulator is around 96% efficient when at full load. Looking at the output voltage of the 12 volt regulator, we can see that the initial rise in output voltage seen between 0 amps and 1.5 amps suggests a negative resistance within the controller, which is due to an incorrect compensation network. However, when looking at the efficiency, we can see, similarly to the 5 volt regulator, that it is more efficient at a higher power, being roughly 95% efficient at full load. With these results, we can happily say that the regulators are correctly controlling the voltage rails despite a couple of abnormalities caused by some incorrect component values. These could have been recalculated and changed if project progress hadn't been stopped.
The software's functionality can be demonstrated by running the embedded code on an Arduino compatible platform. When the connect button is pressed, serial communication is established between the computer running the control program and the microcontroller. It does this by sending an identity request to all the USB devices connected to the computer and automatically finds the COM port that belongs to the ROV. Once connected, the control program arms the thruster's ESCs and starts requesting sensor readings. The actuators can be toggled via buttons on the control panel or by using the controller with key bindings. The thrust vectoring algorithm, which converts joystick movements into thruster speeds, was tested using the ROV test jig in a container filled with water to verify that 6-axis control can be achieved. The COVID-19 pandemic has had a profound impact on our ability to complete the project. Whilst we were able to design, manufacture and test multiple revisions of each PCB, certain restrictions meant that we could not test the electronics control system in the environment it was designed for. Restricted access to manufacturing facilities meant that we could not manufacture the ROV chassis to mount our system to, and we were not able to complete the development of the surface control station. Unfortunately, the MATE ROV competition was also cancelled, meaning we were not able to put our design to the test. In conclusion, we believe this project has been a massive success and a learning experience for all of us. We mostly met the initial aims we set out to meet and have exceeded them in some areas. Whilst we won't be competing in this year's competition, we hope future teams will continue our work. Thank you for listening.